Thanks for joining us today. I'm Chris Ruoff, the publisher of Charged. Today's webinar is about improving the energy density and performance of EV battery packs with thermal management and coatings, and it's brought to you by Lord Corporation. After the presentation, there'll be a Q&A session. Please submit questions you have at any point during the presentation by clicking the Q&A button at the bottom of your screen. Also, the recorded video of this presentation will be available to view at any time after the presentation is completed. So we'll send you a follow-up email that contains the links to watch that video. So at this point, please welcome Nick Capelli, from Lord Corporation.
Hi, everyone. Thank you to Charged for partnering on this presentation, and thank you for tuning in to today's webinar on improving energy density and performance of EV battery packs with thermal management and coatings. My name is Nick Capelli, and I will be today's presenter. I started with Lord Corporation in June of 2015, immediately after graduating from Penn State with my chemical engineering degree. I've been working as an application engineer with Lord for the last 2 years. Here's what we'll be discussing in today's presentation. I would first like to start with a little bit about Lord Corporation, and then I will move to our electrification solutions, focusing mostly on thermal management materials and coatings. Finally, at the end, we will be having a Q&A. Lord Corporation is a privately held technology and manufacturing company that is 95 years old. We currently employ about 3,100 employees in 26 different countries, so we are a global company. Our corporate headquarters is located in the Raleigh-Durham area of North Carolina, but we have plenty of offices around the United States, including people like myself who are in the field. Half of our company is mechanical, and the other half makes materials, like those that we will discuss today. We cover a number of markets, but today we'll be focusing heavily on the automotive market, specifically electric vehicles. And as I mentioned earlier, we will be discussing our thermal management materials and coatings for these applications. Here is a map of our global reach. The materials that we will be discussing today are currently made in the United States and in China, with a manufacturing plant also currently being built in Germany. We also have R&D centers throughout the world, which can be seen here on this map marked in the smaller red dots. Moving to our electrification solutions, we offer the following 5 technologies: thermal management, structural adhesives, coatings, smart valves, and sensors. The first 3 listed in the top row are part of our performance materials division at Lord, and the last 2 in the bottom row are part of our dynamic systems division, otherwise known as our mechanical and electrical part of our business. As I've mentioned, however, today's conversation will be specific to our thermal management materials and our coatings. So let's start with thermal management. Lord's line of thermal management materials falls under the brand name Therm, and we offer 3 main material categories under this brand: potting materials, adhesives, and gap fillers. Potting materials, also known as encapsulants, are low viscosity materials that are developed to fill space in and around electronics to dissipate heat, insulate electrically, and provide protection from the environment, whether that means the protection is from chemicals, dust, vibration, shock, or anything else that may be needed. Adhesives are typically thixotropic or high viscosity liquids that maintain a high bond strength to mate 2 surfaces without the need for mechanical fasteners. In the Therm line, they combine the benefits of structural support with thermal conductivity. Finally, gap fillers are materials that dispense like adhesives, but have mechanical properties closer to the potting materials. They're used as interfaces to quickly transfer heat from hot electronic components to heat sinks. Unlike adhesives, however, these gap fillers do not have high adhesive strength, so while they can be used to assist in structural support of these applications, they should be coupled with adhesives or mechanical fasteners. One thing on which we pride ourselves greatly at Lord is that we can offer multiple chemistries from our Therm portfolio. As you can see from the table, the 4 different chemistries, silicones, urethanes, epoxies, and acrylics, all have different benefits and limitations. So we can recommend a chemistry that will pair well with your application instead of trying to force a material to work for an application where it will have no chance to succeed. We offer potting materials in silicones, urethanes, and epoxies, adhesives in all 4 chemistries, and gap fillers are offered as silicones and urethanes. Moving to discussion on electric vehicles, batteries are the components within the vehicle that have the most impact on EV reliability, range, and cost. So thermal management of battery packs is of utmost importance. Starting first with range, the higher the temperature of the lithium-ion cells within the vehicle, the faster the degradation of the material inside the cells will occur. As those cell materials degrade, the cell loses its ability to hold as much charge. So as this degradation happens across the entire battery pack, you would see a decrease in your car's range. With thermal management in a vehicle, however, that process will be significantly slowed since these materials help to keep the batteries in their ideal operating temperature range. Concerning reliability, high temperatures in lithium-ion cells decrease the cycle life of each charge, meaning that the cells will have to be charged more frequently. And again, as these cells heat up, the materials inside the cells will degrade. In some extreme cases, without thermal management, thermal runaway can occur, which can engulf the vehicle in flames. This obviously puts a damper on the reliability of your car. The same value proposition applies to power electronics and motors. In the coming slides, we'll be discussing how these thermal management materials should be used within EV applications and the implications they have on range, reliability, and cost. We'll start with a comparison of two common thermal interface materials found in EV battery packs: gap fillers and thermal pads. In practice, battery manufacturers typically use one of two types of TIMs, either a cure-in-place liquid-dispensed gap filler or a pre-cut thermal pad. The video on the left shows a gap filler being dispensed. Gap fillers are often applied by meter mixing a two-part system, dispensing on one of the two substrates, and pressing the two substrates together to reach a specified thickness. The material is then allowed to cure to form a solid but compliant interface. Thermal pads, on the other hand, are pre-cut to a desired shape, applied to one substrate, compressed down to a set thickness, and fixed in place. The applied compressive load forces the solid yet compliant pad to make intimate contact with the rough surfaces. The amount of pressure applied to the pad can have a large impact on its thermal resistance. We've discovered that customers are confused about which type of TIM to select, so we took it upon ourselves to perform a careful study comparing the thermal performances of these products. Here's the outline of the experiment which we conducted. The goal of this experiment was to compare the thermal impedance of the previously discussed gap fillers and thermal pads, labeled in pink as TIM, to see which technology is superior in maintaining low thermal resistance or described as better heat transfer. These are the four different materials that we tested. We picked two of our gap fillers, Cooltherm SC1200 and Cooltherm SC1500, which have thermal conductivities of 2.0 and 3.8 watts per meter Kelvin respectively. We then searched for gap pads that had similar listed thermal conductivities of 2 and 4 watts. We picked varying thicknesses of gap pads because these are the gaps we typically see in EV applications. For this experiment, we used an ASTM D5470 certified TIM tester from Analysis Tech. This piece of equipment functions by calculating thermal conductivity after measuring thermal impedance. First, the thermal impedance of the copper discs was calculated, and then the resistance of the interface between the copper substrates was calculated. This was done at different pressures and using a 200 centistoke silicone fluid as the medium to wet out the surfaces. Once these values were known, the thermal impedances of the thermal pads and gap fillers were calculated by finding the impedance of the whole system and then subtracting the known impedance of the copper and copper interfaces. This thermal impedance was measured over a range of pressures for the thermal pads, but since the gap fillers do not need pressure to be applied, the gap fillers were measured at the lowest possible pressure. From there, we calculated the thermal conductivity of the samples. Using the TIM tester shown on the previous slide, we measured the thermal impedance of the setups. As you can see from both the graph and the table, the gap fillers had significantly lower thermal impedance, with the Cooltherm SC1500 having an impedance 5.1 times lower than the thermal pad with the same advertised thermal conductivity. Also seen during this test is that the thermal conductivity of the 2 watt gap pad wasn't close to what's advertised, measuring as only 1.3 watts per meter Kelvin. Seen in the previous slide, the thermal impedance of thermal pads is significantly higher than in the gap fillers. This is a result of lack of conformation to the surfaces both at a micro and a macro level. The pictures on the left show that the gap pad will not conform to the surface imperfections, whereas a liquid dispense gap filler has no problem doing this. Also, on the macro scale on the right, manufacturing tolerances show us that there will be a limit to a thermal pad's ability to conform to the cells, whereas once again, the liquid dispense gap filler does not have a problem with this. In practice, the only way to ensure that the thermal pad will conform is by adding pressure to the application. Here, we examine the effect of pressure on the thermal impedance of the thermal pads. The x-axis measures pressure ranging from 50 to 650 kilopascals. And then thermal impedance is measured on the y-axis as a function of pressure. As you can see, a significant amount of pressure had to be applied to lower the thermal impedance of these thermal pads. In our experiment, whenever that significant amount of pressure was applied, we actually saw the pad squeeze out of the TIM tester, as evidenced by the picture in the bottom left corner of the graph. In all applications too, no matter how flat they appear to be, there will always be some sort of manufacturing tolerances. The picture on the right illustrates this. If you have a 0.5 degree angle going the length of your battery pack heatsink, the thermal pad, which will have a predetermined thickness across the pack based on the pressure applied, will transfer heat much more efficiently where it has been compressed to a thinner section. But as the pad gets thicker down the battery pack, the pad will take more time to transfer heat out of the cells. Thus, the cells will operate at a higher temperature the farther down the pack they are. This will lead to earlier failures in those cells, decreasing your range and reliability. Here we've combined the results from the previous two slides, examining the effects of pressure for the different thicknesses of thermal pads. The x-axis is the recorded thickness of the gap pad or gap filler, and the y-axis is the resulting thermal impedance. So the thermal pads here, shown in black, are tested at various thicknesses, achieved by compressing at varying pressures. The gap filler, shown in red, is tested at varying thicknesses by curing in place with different standoff heights. The graph on the left shows the 2-watt thermal pad versus the Therm SC1200 gap filler. And you can see that the same thickness, the gap filler has a much lower thermal impedance than either thermal pad. The gap filler can also fill much smaller gaps than either the 1mm or 2mm pad can be compressed to. The graph on the right shows the 4-watt thermal pad versus the Therm SC1500 gap filler. And again, you can see the gap filler has much lower thermal impedance at the same thickness. You can also see that these 4-watt thermal pads were actually much more difficult to compress below their nominal thickness because they have much more ceramic filler in them. So they're going to be able to cover even less tolerance than the gap filler is able to. Also, the slope of the black thermal pad lines is much higher than the red gap filler line, which shows that the bulk thermal impedance rises much more quickly as the thickness increases for the pads than it does for the gap filler. So in conclusion, gap fillers are able to cover a wider variety of gaps and have much lower thermal impedance than the thermal pads, even when they have the same or higher bulk thermal conductivity. After this preliminary work, we started phase 2, which was to test the gap fillers and thermal pads in more real-world conditions. So we partnered with the National Renewable Energy Lab, also known as NREL, located in Colorado, who has a lot of experience with performing thermal testing and building battery packs. NREL helped us to build an EV battery module using 5 Samsung cells and a liquid cooling plate. Our 2-watt Therm SC1200 was put between the cells and the cooling plate, as was the 2-watt thermal pad, and then the entire setup was placed in an environmental chamber. Outlined here are the test parameters. The thermal pad was applied with as little entrapped air as possible, and the gap filler was applied with each cell getting its own bead of gap filler underneath. Shims were also added to mimic manufacturing tolerance, and then the cells were compressed to 34 kilopascals. The cells were then equilibrated to 30 degrees Celsius, and the modules were charged at 150 amps while temperatures were tracked. The results of the test are displayed here. For each TIM material, we included a variation with shims on cells 2 and 4 and without shims on cells 2 and 4. The rightmost column in the table displays the amount of heat removed by the coolant, and as you can see, in both instances, the gap filler removed over 50 watts from the assembly, whereas the thermal pad did not. The gap filler without the shim removed 23% more heat than the thermal pad in the same setup, and removed 49% more heat than the thermal pad when the shim was included. In conclusion of this study, you can see the head-to-head comparison of thermal pads and gap fillers. The big picture to take away from our lab study and the study we conducted with NREL is that gap fillers provide superior performance to thermal pads. Regarding cost, because thermal pads often have to be cut to specific shapes for their applications, the cost is higher and it results in a lot of scrap, whereas the gap fillers can be dispensed in any shape or pattern without that excess scrap. Regarding air entrapment, I like to equate thermal pads to applying tape or a screen protector on your phone. How many times in your life have you tried to do this and you found that you got an air bubble or a crease under it or just any imperfection that made your screen protector or your tape not completely flat? The same idea applies for thermal pads, except those air bubbles will then significantly affect heat transfer within your application. With gap fillers, however, the liquid dispense nature of the product displaces the air within the application, so that any air entrapment is negligible. Our white paper, liquid-dispense gap fillers versus thermal pads, a case study on thermal performance, goes into detail about all the points on this slide, so please feel free to read that at our website at lord.com. And with that, we've finished the thermal management materials portion of this presentation, so now we'll switch gears and move to the coatings portion of the webinar. We've recently discovered 3 major reasons for why EV companies are so interested in coatings. The first is lightweighting. Everyone wants to make cars lighter to get better range and/or decrease cost. The second is flame resistance. EV battery packs are susceptible to fire, so any way to mitigate that or slow down the flame is of interest to EV battery pack manufacturers. The third and final reason is replacement of the films used to wrap batteries for electrical insulation, because they can entrap air, are difficult to use in large volumes, and are expensive, whereas a coating will not have these same issues. Speaking first on Cipiol FR, this is a coating that I really like, partially because I was involved in its initial development in one of my previous positions at Lord. This is an intumescent coating, meaning that as it is exposed to heat, air or a gas will form inside the coating, causing it to expand. And since gases are such good thermal insulators, this will significantly delay the transfer of heat to the surface below the coating. What's great about this coating is it can be used in 4 major ways on EV battery packs. The first is to coat the outside of individual cells to prevent fires from spreading from one cell to the next. The second is that it can be used to coat the inside of individual module boxes to then prevent fires from going from one module to the next. The third is that it can be used to coat the inside of an EV battery box to then prevent fire from going inside the battery box to the rest of the car. And finally, number 4, it can be used to prevent fire from getting into the car if there's a fire on the outside. In addition, the coating can be used as a lightweighting tool, allowing OEMs to continue to use aluminum, but then by coating it with Cipiol FR, getting the additional high temperature performance that aluminum currently lacks. Here we have a video of the performance of bare aluminum compared to Cipiol FR coated aluminum when exposed to a flame that is over 1200 degrees Celsius. As you can see, the aluminum is already beginning to be effective, and within 1 minute, it will actually start to melt. And at that point, the aluminum has now broken through to the other side. You can see, however, with the time lapse on the right side, Cipiol FR coated aluminum has now withstood 8 minutes, 9 minutes, and finally 10 minutes of flame testing. Here's the back of the regular aluminum, and now there's the back of the Cipiol FR coated aluminum, virtually unaffected after 10 minutes under flame. Here we have a comparison of uncoated aluminum and Cipiol FR coated aluminum when exposed to a 30-minute burn test, so a test that was 3 times longer than the video that you just saw. As you can see, the temperature of the uncoated aluminum spiked very quickly, reaching over 800 degrees Celsius in about 2 minutes, whereas all of the different thicknesses of the Cipiol FR coating maintain the temperature of the aluminum below 300 degrees Celsius over the entire 30 minutes. Since the melting point of aluminum is around 660 degrees Celsius, this means that adding even just 25 microns, or about 1 mil, of Cipiol FR can prevent the aluminum substrate from melting when exposed to fire. This graph highlights only the Cipiol FR coated substrates from the previous slide to allow for more clarity for the performance at different thicknesses. In this graph, we used logarithmic trend lines to smooth out the appearance of the data. As expected, the thickest coating provided the greatest resistance to the burn test. But to reiterate, none of these trials exceeded the melting point of aluminum. The 25 micron coating maintained a temperature under 300 degrees Celsius, the 89 micron coating under 250 C, and the 137 and 191 micron coatings maintained temperatures under 200 degrees Celsius. Moving to dielectric coatings, we have seen 2 major contenders in the EV space. The first is our JMC 700K. Lord JMC 700K is a coating that was originally used for rare earth magnets on motors to protect from corrosion. But since introducing it to the EV world, we have seen applications in heat sinks to be used as an extra dielectric barrier between the cells and the cooling plate. The second dielectric coating is Civiol UV, which is a UV cured coating currently in development at LORD, which is intended to replace the films on individual cells. This, like JMC 700K, may also be used as a dielectric coating on cooling plates, but with the benefit of extremely fast curing for higher throughput. Before we conclude, I'd like to mention that LORD Corporation will be exhibiting at the Electric and Hybrid Vehicle Technology Expo from September 10th through 12th, 2019 at booth 1111, so very easy number to remember. We'll also be demonstrating live gap filler dispensing at the booth, so please feel free to come check us out. Also, Dr. Dan Barber, one of our staff scientists, will be delivering part 2 of this talk that Wednesday morning. This presentation, titled Staying Cool, Thermal Management Solutions When No Two Battery Packs Are the Same, will explain how customization with battery technology will then require customization of thermal solutions and the impact that those custom solutions will have. If this interests you, please go see him and ask any questions that you'd like. In conclusion, thank you all for listening in today. I hope this webinar was very informative, and here's my contact information with my email listed below, so please feel free to ask me any questions you have. With that, I guess we'll transfer into our question and answer session. Thank you once again. All right, so the first question that we have is related to the air entrapment of gap fillers. And the question is, how prone are gap fillers to air entrapment, and how might this affect heat transfer? So because gap fillers are liquid dispensed, they are very good at displacing all of the air within the application, so the effect of air is going to be negligible. So heat transfer will be maximum whenever you're using these gap fillers. The second question that we have is, how do gap fillers handle high vibration applications, and is there any degradation of performance? So gap fillers can be susceptible to vibration, and as a result, what we like to do is involve ourselves in the design process of these battery packs or these applications, because while gap fillers do help damp vibration, they're not adhesives. So they don't have high adhesive strength. So in helping you in the design phase with these gap fillers, we can make sure that our gap fillers in a way will be protected from this vibration so that there's no concern about delamination or degradation of the performance, because obviously you want the maximum thermal conductivity or the least thermal resistance in your application as possible. The third question we have is, how does dielectric strength of gap fillers compare to that of thermal pads? So from a chemical perspective, the materials that are used for thermal pads and gap fillers are going to be the same. So if you have a silicone gap filler or a silicone thermal pad, they're going to have the same general dielectric strength because of the nature of the chemistry that's used. Now, with that said, thermal pads do have the ability, because they're pre-cured, to add a dielectric layer in there. So the way to combat this with gap fillers is that we would recommend combining a gap filler with one of the dielectric coatings that we provide at LORD. Question number 4 is, how widely are gap fillers used in battery packs currently? And while I can't give you exact details, LORD Corporation currently works with a number of OEMs who have gap fillers in their battery packs that are being used in production. Question number 5, does thermal conductivity vary based on the thickness of the bond line? That's a good question. So thermal conductivity is a bulk material property, so it does not vary. However, the amount of thermal resistance going through an entire system would change because of bond line. So the thicker the bond line, the longer it takes for the heat to transfer from one place to the other. So a thinner bond line will transfer heat faster than a thicker bond line would. Question number 6 is, must Cipiol FR be spray applied, or can it be brush and dip applied as well? One of the particles in Cipiol FR does settle, so we typically recommend using it as a spray application. With that said, though, I know there's been experiments done on brushing and dipping applications, and this is something that we can talk about more. So please feel free to email me about that question, and we can put you in contact with one of our scientists who's doing the experiment right now. Next question is, how does adding the Cipiol FR to the design reduce cost in battery packs? This is going to be related mostly to lightweighting. So in a battery pack, you could use a composite roof instead of your typical aluminum roof. That's going to give you a weight and price reduction. And then by coating it with the Cipiol FR, you can increase the heat and flame resistance of that composite. The next question, what are the challenges by using some of these solutions with prismatic or pouch cells? So we found that you can use gap fillers in all three cell geometries, whether that's cylindrical, prismatic, or pouch cells. So there isn't really any concern with the geometry that you're going to be using. All right, the next question is, do gap fillers need high flexibility for thermal management applications? This is going to be design dependent. So it's really about how well does your application change with the material. So some applications will need a very flexible material just based on how they're designed. Other ones, they can use a harder material because they don't plan to have that much movement in their application. So that's going to be just very design specific. But most of our gap fillers are very soft materials. They are flexible, but we do currently manufacture some that are urethanes that are a little bit harder and they act more like an adhesive. So they're still considered to be a gap filler. This is again related to Cipiol FR. So how is Cipiol FR applied, and does it require special breathing gear? So whenever we use this material, like I said, it's typically spray applied. This is with a pneumatic gun. And then concerning special breathing gear, we typically would do this underneath some sort of fume hood. So we would recommend ventilation when using this coating. Yeah. So again, another question about Cipiol FR, can it be applied to composite structures? And the answer is yes. Okay. Another question here is, do gap fillers substitute epoxy potting for battery packs? So I think what that question is trying to get at is, can you use a gap filler instead of a potting material for battery packs? And the answer here is it depends. So you would need to know where the heat is going to be most generated in your application. So say that most of the heat is going to be generated from the bottom of the cell. Well, in that case, a gap filler would be fine because that heat is going to be transferred straight from the bottom of the cell through the gap filler and then into the cooling plate where it will disperse. Now, if you decide that you need more vibration protection, or your heat's being generated from somewhere else within the cells, or you'd rather the heat be transferred to the size of your box or whatever it is, again, it's application dependent, then that's when you may want to use a potting material instead of a gap filler. Okay. Next question is there any specific method for applying the gap filler to a surface? So for prototype builds, what we typically use are pneumatic dispensing guns with these materials in cartridges. So most of our gap fillers come in 50 milliliter, 200 milliliter, or 400 milliliter cartridges. And because they're very high viscosity, they're thixotropic, they can be kept in those cartridges without the filler settling. So again, for prototype, we would use hand dispensing. But then after that, in the full production phase, we would recommend using MMD equipment. Meter mix dispensing equipment is its full name. And that has two reservoirs of material. And then those materials, the resin and the hardener, are pumped up to a static mixer, at which point they are mixed together and then dispensed onto the application in your desired shape. This is usually done by programming some sort of robot to make the pattern on your cooling plate or whatever the application is. Okay. Another question is, what other substrates can be used with Cipiol FR? Is it specific to aluminum only? And no, it can be used for metals and composites, plastics, so a number of substrates. Another question is, what is the typical curing time of gap fillers? So for most of our gap fillers, we recommend a 24-hour room temperature cure. However, this can be accelerated with heat, and the general rule of thumb is that for every 10 degrees Celsius that you increase the curing temperature, the curing time will be cut in half. Now, some of our materials, if you don't need your full cure, absolute full cure, but just need handling strength, this can be sometimes within a number of hours, single-digit hours, for you to move on to your next application. But the full cure is about 24 hours at room temperature and set up with heat. One of the, and this is the last question here, is there any smoke or toxicity data for the Cipiol FR coating? And from the inception of this coating, there were three specs that it had to pass. One was a resistance to heat, one was a smoke density test, and then the last one was a toxicity test. And the idea for the original application was that it would be used on subway cars to prevent people from suffocating on the smoke that would be generated in a subway fire, because they would have to be, they would be stuck inside the subway car, and if they couldn't get out in time, obviously in a tunnel in the subway, you need to make sure you're giving people enough time to get out of that enclosed area, as well as to make sure they won't suffocate on the smoke or be negatively affected by any toxic volatiles. So in this case, this coating was tested specifically to a standard that was addressing toxic chemicals. I don't know what it is off the top of my head, but this is something we can get you that information about. So if you have a question about that, please do ask me, send me an email, and I'll get you that data. Thank you, everyone, for attending.
Great, thanks, Nick. This is Chris from Charge Magazine again. I'd like to thank Nick and Lord Corporation for the presentation. And as a reminder, this presentation was recorded, and we will send out an email later today with a link to watch the recording again. And the email will also contain Nick's contact information if you have more questions. So again, I appreciate everyone attending, and thank you for the great Q&A session.